Uh, Thank you, Katya. Thank you for the invitation, and thank you for the introduction. Uh, so I'm going to tell you a little bit of different type of problems. So this is a kind of a la carte of variations of problems that are connected to free boundaries and comes from the area of inverse problems, taken from inverse potential theory and scattering theory, transmission, conductivity, and all these things. And there seems to be all leading eventually to kind of free boundary problems. And since free boundaries are people have developed a lot of tools, especially concerning regularity theory, for solutions and also for the so-called transmission boundary or scattering boundary. It seems that these tools might be, and they have already been pretty much beneficial to the theory and linking them together. So let me just tell you a minute about my background. I started my PhD, I think it was 87 sometimes, with Harold Shapiro at KTH Stockholm. And we did potential theory, inverse problems in potential theory. And my thesis was about quadrature domains that are kind of mean value properties of different type of domains, not necessarily with the mean point value, but measure value. And that led to eventually free boundaries, and those connections have further developed a lot in the last 35, 40 years. So this could be a picture of what I'm doing, what I've been doing all the way until here, and I will tell you a little bit about the systems we are looking at nowadays. So let me see if I can make a yes. So here is the list of things I'm gonna do and talk about. So the free boundary transmission and inverse conductivity and the inverse scattering problem. Okay, and you can of course see the headings up all there, and these are the subheadings basically. So what is a free boundary? So in lay terms, it's an interface that is at the beginning unknown, and they may come from the, like if you minimize a functional and the functional as a source term or an extra term than the Dirichlet energy, then this might be discontinuous or continuous but not differentiable, etc. And they usually lead to an interface where the discontinuity in the term appears. I will show you soon one or two of these integrals. And phase transitions are, of course, the most common, creating free boundaries. And then there is a qualitative change of the medium that gives you this free boundary. So there is a stress between the two systems, basically. Here I have in the footnote, you can see when ice melts to water. So that's a phase transition, and the region, the mushy region, you can think of a very sharp region, like very smooth region, but of course it's a mushy region. That's a free boundary. Liquid to crystals. When you buy and sell assets, the regions between them, they are actually free boundaries. You can think of biology, active and inactive, or active to inactive. All these things are, you have the coloring games, blue to red. You can think of discrete versions, and also disorganized to organized, kind of discrete criticalities are all producing free boundaries of very, I mean, this is diverse areas, and they all will come back to one thing, and that's the free boundary, an interface that is unknown. And so here's the simplest one. So think of a non-negative function, and you have a boundary value. Let's see if I can write also for you. Doesn't like me to write. Okay, I don't want to mess up, so I don't write. So you take the unit ball, take boundary values that are positive, and then try to solve this problem. Laplacian of u equals to 1. If boundary value is very small, and then you will see that you don't get solutions that are non-negative. Solutions prefer to go down below 0. At the end, you put a constraint. You say, no, don't go down to the 0, below 0. Then it produces a level which is 0. If we do that with minimization, for instance. And that creates a 0 set, which is called coincidence set. The boundary of the 0 between 0 and the positivity set is a free boundary. There's a lot of pictures you can see. I should probably have put a picture for you here, but so here is the functional you're minimizing. So f could be in the previous case, f could be u plus the positive part of u. So take maximum of u and 0, and then you will have. Sorry, I meant the capital F here. So you can have a general f. In another case, it was the Heaviside function. In the former case, it was the Heaviside function here. So this is a Heaviside function, or the characteristic function. So in general, this guy here is not differentiable. Then you produce a free boundary. The worst case is when f itself is discontinuous, which I think might be my next slide. Yeah. So if f itself is discontinuous, capital F now, I mean, then you actually, so the little f, when you take the Laplacian, I mean, you go to the PD or the Lagrange equation, you will have a measure, and that messes up everything. And then you have a balance between the positivity and negativity part. If there is no negativity part, you only have the gradient being 0, constant. And so these are type of free boundaries that are produced. So let me do it again, because I know some of you may not be familiar with this. So I run the slides again. So you start with the one example like this, and now you can think that this is our little f, and that can be variations, a lot of different f's. And here is the example. And now the previous one, you want to take the primitive of this little f, capital, and then minimize this functional. Then you will get a solution to this PD. It's a semilinear PD. Of course, the semilinearity here is f is usually non-negative, so or even sometimes monotone. But that creates a kind of a region when the function might be completely 0, and then there is a region which is positive, and the boundary between those are going to be the free boundary. So I hope the message is now clear. The one problem that is also connected to transmission problem, which is more connected to transmission problem than the obstacle problem, is exactly when capital F is the characteristic function. Not little f, but the capital F is the characteristic function. So when you take the Euler-Lagrangian, then the right-hand side of your Laplacian will be a measure. And the measure is exactly in the transmission problem. When you go from one side to other side, there's a balance between the gradients, if there are two sides. In general, free boundaries don't need to have two sides. One side could be completely 0. So these are a little bit different. The one that is 0, one side is 0 and one side is positive, is connected to conductivity problem, for instance. I will come to that later. So this leads, when you get this kind of measures, the measure is exactly as I just mentioned, the balance between the gradients. That's the transmission problem. And that balance is given by something like this. In what we call Bernoulli problem, this is a kind of latent heat in the famous Stefan problem. So there is a latent heat. basically. Let me not go into that. And this is the very general Bernoulli problem. So you can think of two PDEs, completely different PDEs, one in the positivity set, one in the negativity set. Now you can think of the transmission problem having two sides. You have two different even PDEs, and then you have the balance between the positive and negatives in terms of the gradient. So this is the normal derivative here. When everything is smooth, this is the normal derivative. There is actually a recent paper that connecting inverse conductivity to this problem, to Bernoulli problem, through scattering approach. Which I don't mention here. I'm sorry for the authors. I should have probably mentioned that. This was written before the paper came out. Okay, so this is another free boundary problem, which is more connected to the transmission problem, actually. I will discuss a little bit of this also. So I'm not going to discuss the free boundary problems itself, but I'm going to discuss the things that are bringing them to the free boundaries. So the main questions that we're interested in, at least I have been interested in the last 30 years, is whether the solutions are optimal in each cases. I mean, you come up with a free boundary problem, I want to see optimality of the regularity. We know that PDEs usually produce optimal regularity, like if you have Laplacian of u equals to something which is smooth, then you get smoothness of the right-hand side plus 2. The Laplacian sort of brings down 2. So if the solution has 2 better regularity. But you're also aware of if Laplacian of u is only continuous, then u is not necessarily even C11, let's say C2. So free boundaries, nevertheless, actually produce this optimal regularity. They have this extra ingredients built in the system that gives you basically always, the optimality of the solution. Like if Laplacian of u is a characteristic function at the beginning I mentioned for you, then you don't expect that u to be C2. Do you expect u to be C11? And for the obstacle problem, the answer is yes, because the right-hand side is monotone. That monotonicity gives you actually regularity, more regularity than in usual PDE. The second question is, well, what kind of conditions you can find, or under mild conditions, you're expecting smoothness of the transmission or of the transmission boundary or the free boundary in our case. So these are the main questions I'm gonna all the time coming back to and mention results that we've got in this connection. So let me start with something that probably most of you attending this seminars are aware of, is the classical transmission problem. So you want to solve this, I don't know how you do that. Then you have a solution to this PDE, and then once you go across the domain D, so D is given domain, bounded domain, once you go across, then your conductivity is changing. Excuse me, I got a little bit. I'm sorry. So you go to cross the boundary of D, then you get a different conductivity than you were outside this. This, of course, already means if you just integrate by parts, in the very simple case, 1D case, you will see that you have a jump between the gradients, and that jump is defined exactly through A and B, if it's just 1 point, one-dimensional problem. You go to higher dimension, that becomes a little bit more harder, and the boundary of D, regularity, all these questions. I mean, D is given from the beginning here. So then the regularity of D will tell you a little bit more about the regularity of U. Okay, so let me repeat that again. We know that if you put something like this, put together something like this, with a given D, smooth A and B, and the smooth boundary of D that's given to you, then you can say something about regularity of U. And you can get the optimality of regular U is not across, but up to the boundary of D on both sides. It has to do with regular the boundary of D is. These are all classical results. Nevertheless, this is not a free boundary. So let's say we can play around with this and make it a free boundary. Suppose you have a system where the system feels to sort of jump starts some kind of reaction, more reaction. And the reaction comes from U itself. If your value goes above 0 or larger than some constant, then the conductivity is changing. So your conductivity changes once you go above a certain value. Here I just put 0 value. Or let's say once your gradient conductivity becomes smaller, then you again jump a new kind of conductivity. So this already gives you a free boundary. So it means that you don't know what D is. The domain D is unknown. Contra to what was known here, and smoothness of D gives smoothness of U. Now here, the domain is unknown, and you only have the system with D being something like this. What can we say about the U itself to start with? And next would be, what can we say about the transmission boundary? You see that the questions are qualitatively very different now. Okay, so these are applications. Well, this is for me would be just reading this. So this appear in kind of in many applications. We have to dig up applications that really bring up this. These are maybe not relevant for our discussions, but yeah, I mean you can see some literature that I have cited here. So I'm not an expert in the application, so I would just repeat what they have said. If you have interest, you can go and look at those papers. From an application point of view, actually, they're interesting, but from a mathematical point of view, they do less mathematics. So let me go back to the problem. And now I just replace D with this, because that's what it is. And now, if A and B are constants, okay, so I'm going my first class in PD. If A and B are constants, I can cook up this function. I just put them together like this, and then you see if you apply Laplacian to V, then you're applying Laplacian to this, and you rewrite this, it will be exactly this equation. Okay, so trust me, this is correct. So Laplacian of V is exactly divergence of this, and it is 0. So Laplacian of V is 0. So V is a harmonic function. Now V being a harmonic function, it is analytic. The level sets of V, the zeroth level set of V, is going to be the 0 level set of U as well. So everything that V tells you, that has to do with U. So whatever you want to find out about U, you analyze V. Now V is at least C1, let's say, then you know that this guy is C1, but since you have cut U with a plus, it cannot be C1. So it has to be Lipschitz. So this already tells you that U is going to be Lipschitz. That's the solution. That's the answer to the question that we didn't know from the beginning. But this tells me that in the constant case, A and B are constant, this problem, this free boundary transmission problem actually gives you a Lipschitz regularity. Now, how smooth are the free boundaries of the 0 level set? It has to do with the classical problem of whether the gradient of V is 0 or not. If gradient of V is not 0, then you get C1 alpha, and then you can start looking for further regularities, etc. But we know that harmonic functions could be like x times y, and the 0 set can be a sort of a cross. So there are singularities. We can analyze also singularities. Okay, this was not a big deal. So let's change A and B. So let's make them non-constant. And then we realize very fast that this is going to be pretty messy. And you can actually make it even more nonlinear. So play around with a very general scenario like this and try to study these problems. So this is something we did with Jian Li and Sang and Kim, who was a PhD student at that time for Kyeonli in South Korea. So main questions would be smoothness of U, smoothness of the boundary of the positivity set, and then if there are singularities for the boundary, how is the structure of that singular set? Could we put a theory like the function for harmonic functions? So the literature is actually rich, and you can go back to Caffarelli and Stefanelli in the parabolic versions, Anderson, my former student, and Michaelian, who I mentored at some period. They also worked together, and the smoothness is related to free boundaries. You have Caffarelli, De Silva, and Savin. They worked on it in dimension 2, Lipschitz dimension larger than equal to 3 also, non-Lipschitz regime. Well, there are a lot, Suave and Amaral and Teixeira and Pimentel and Schweich, and there are more. So these are all from the theory regularity of the free boundaries. So there's because this is really now a free boundary. It's not only a transmission, but a free boundary problem. Okay, so with Kim and Lee, we proved that so A plus and A minus now are Holder functions. The right hand side is Holder, and then we proved that actual solutions are Lipschitz. We had two different methods to do this. One method was using monotonicity formulas, which was probably big machinery, and then they find out that with freezing coefficient, we could do this much easier from a PD perspective. We proved the C1 alpha regularity of the boundary of the regular part. I called it regular, then it means that the gradient is non-zero. But of course, since the function is only Lipschitz, the gradient doesn't mean much here. So you have to work with kind of integral mean of the gradient of the function U divided by R, and the distance to fair boundary, and then prove that it's going to be C1 alpha once that's not zero. Then there is a structural theorem. So we could line up a series of results which goes very parallel to the class of harmonic functions, because all this theory exists for harmonic functions. The difficulty was, of course, to get the Lipschitz, and then we could bootstrap with the further new results. Key ideas. So key ideas to prove that is you get first the Georgi, because you have a divergence type equation with the coefficients that are bounded. So the Georgi tells you actually your solutions are going to be Holder. And then since you have Holderness, you can start working with it and at least have some good continuity. And then you use a standard blow-up technique in free boundaries. This is a very standard technique. So you say if it doesn't have Lipschitz growth, then you start blowing up, scaling and scaling, getting a limit function, global solution, and you come up with contradictions. So this theory has been there for free boundaries the last 30 years. But usually you don't get optimality. That's the problem with blow-ups. But you get C1 almost. So it's not Lipschitz, but it's below Lipschitz, a little bit. So anything below Lipschitz, this is given to you. That has to do with if you have a function which grows sublinearly, and it is zero at the origin and let's say non-negative, just for simplicity, then, if the function grows sublinearly and the function is zero at the origin and it is harmonic, then it has to be, of course, constant. That's the whole idea you bring from standard PD. Then you get this by blow-up technique. So once you have that, you can actually, so this was an idea actually by Sung, and first I thought it was wrong, and then I came back after a month and said, well, it is correct actually. So we could push this. So you freeze the coefficient, let's say origin, and then you freeze that, and you do the same thing that you did in the constant case. So this is exactly like the constant case. But the problem is that A is not constant, but you fix the constant, and you do the same game, Then you get a harmonic function. Oh, no, you don't get a harmonic function. You get almost harmonic. You get divergence of something which is actually something like this. And this is actually very good for us because now Shahgholian theory comes in. Shahgholian theory comes in. Observe that here there is a difference with classical Shahgholian theory because it's a pointwise. I'm saying omega, so this function here is C alpha only at the origin, not in a neighborhood of the origin, because I freeze only one point. So you have C alpha in terms of integral, so it's a 1 point regularity. And you have to run the theory a little bit. I mean, it's not hard, but you have to do the details anyway. And from here, you get basically what you want. And then you get, that's the argument, that's the key idea here. And then you get your regularity, and then you can go further. So this brought us to go further to transmission problem for the P Laplacian cases. And so this is a completely different problem. This is actually, I would say this is an extremely hard problem. So when you have two different P's, and then you say that whether you're in the positive regime or negative regime, you have a different conductivity. But when they meet, there is a balance. But the balance is not given through an operator. If you put divergence, if this would be a divergence type operator, you could still get, maybe with a little bit work, the Georgia type regularity holder. And maybe you could do some kind of work as we did before. But now you have a minimizer. When you have a minimizer, then you have to do everything from scratch. And this took us, I think it took us a whole year to work on this, and we were almost about to give up. So we couldn't even get continuity of this. Existence is, of course, nothing to discuss here, but smoothness of solutions, to start with, even continuity, this seems not to be so obvious how you get continuity of this. So I think I will probably show you what the reason for this is, because if you want to do any regularity theory, even in PDEs, I mean, there are all the variations of methods. One method is kind of scaling method, which I'm more familiar with. Of course, you have the variational techniques also. This is less variational. This also goes for PDEs. But if you would scale it, you can actually scale it differently with the same R, but different values, because you don't know U plus and U minus behave the same way. Because one may go linear, the other one goes sublinear. One may go like distance to power 1/2, the other one distance to power 1/3. They don't balance on the boundary. You don't see that balance from the minimizing functional, the minimizer. You see that when you have a divergence type equation, but when you have a minimizer, you don't see that. So if M is the supremum of U plus, N is the supremum of U minus, then you can actually do a scaling like this to keep UR bounded. You want UR bounded at the level R, so this is the correct scaling. There is no other scaling, and M is the supremum of this, N is the supremum of this guy. But now you see, when you want to go back to the functional and work with it, you see there is a very strange balance here. There is at least a balance, of course, but it is not standard balance. So there is no obvious what we call doubling, because these are techniques that you would need. So I'm at the technical level, I'm apologizing for that. So then there are no monotonicity formulas, and the approximation techniques, all these things are a little bit gone here. So you have to do everything from scratch, and fortunately we could do that, and we could get regularity of the solution. And here is a trying to go to the next page, but it doesn't like me. Okay. Let me go completely. So we could prove that's a holder. Okay, solutions are a holder. Sorry. So we know that solutions are going to be Holder, and that's a pretty big machinery to get there. We did a lot to get to Lipschitz, but we stopped because it was hard to work with that. We didn't have any ideas of to proceed. So this is still an open question. We also could prove that the boundary, the free boundary is actually C1 alpha most of the times. We couldn't get the right measure, but we could get at least one measure with respect to which we get this C1 alpha. So it has n-1 measure, but I would prefer to get standard type of regularity. So we left it here, and it was very hard to come back to it because I think maybe it would need stronger people to come and look at it with persistency. So we left this problem, but so once you go for transmission problem with PQ level, this type of nonlinearities, then things become extremely hard. Okay, so let me tell you one more thing. This is very easy to tell you, but this is very hard to solve. We also left this open. So this is a vectorial transmission problem. Actually, one of my mathematical grandson came to Stockholm for 2 years as a postdoc from Purdue, and we started looking at this problem. And after 6 months, we gave up because it looked like this is a very hard problem, at least for us. So we put so you can think of M being a manifold now. So M is a bounded domain, and with the boundary C2, and once you are inside that, it's a system. So it's a M. Once you are inside that manifold, your conductivity is changing. So when I'm saying inside, when your map is inside, so the pullback is in the domain, and you don't know what the domain is. So if you're pulling this back to Rn, you would not know what Rn is, what this domain is. So this gives you a kind of free boundary. And the reason we started looking at it, one of the reasons, and maybe one of the only reason, was that this was connected to a system problem we were looking at that time when Songmin came to Stockholm. And I was thinking of whether there are transmission problems related to this. I have no idea about the applications of this problem, but I think you might probably find something of interest. And there could be interesting problems, I think, to open up for the future. Okay, so I don't have any results to mention here, but I think the problem itself is interesting. We could prove very slight regularity, but as I said, it's not worth mentioning it here. If you do the same now for minimizer, then you don't even know continuity of this. So you're stuck with starting from the scratch. Even for p equals to 2, I don't see how you get off the ground to get something. The jury doesn't help you here. There is if you are interested in systems for free boundaries, this is part of it also. There is a class of problems. I think we have 4 or 5 papers, one coming in a few days. Also expository a little bit, is that with Figali, Guerra, and Kim, we have a series of papers on archive, you can find them. These give you a little bit of introduction to free boundaries for systems that you have towards manifolds, and they are connected to harmonic maps. So you can think of harmonic maps when there is a constraint of the solutions of the maps. There is also an expository in notices, if you want to see. That's what was supposed to be written for master level students. I think we stretched it a little bit more. It's a very good read for introduction to a system case of free boundaries. Okay, so how much time do I have? Okay, I think I can make it. So let me go to inverse conductivity problems. I will have a little bit messy notations here, but bear with me a little bit. So you start with the potential. So I will have the sigma here is the usual surface measure. So this is the surface measure. And F here is the fundamental solution to the Laplacian, with any other operator, linear ones, of course. And then you have the convolution. So you convolve the fundamental solution. You can also take Green's function, but fundamental solution is good enough for us. And then you have your function f that are given to you. F is given to you. G is given to you. Alpha and betas are dimension dependent, and they are constant to normalize. So you can take your Laplacian of u, and you get this, plus on the boundary, you get a measure, of course. Because Laplacian of potentials, the volume potential is always this, but Laplacian of boundary potentials are going to give you a measure, the measure on the boundary, the function on the boundary. So UD has a Laplacian which looks like this. You can always think the boundary is Lipschitz just to get this meaningful. You can have it in the variations. So what is harmonic continuation property? So suppose you have a boundary point on D, and then you have a harmonic function in a neighborhood of that point. So here in the polar radius 1. So you have a harmonic function in the polar radius R1, let's say, in a neighborhood. But your harmonic function agrees with this potential outside D. So when you're outside D, the potential and the harmonic function, they agree. So this is a kind of inverse problems, and you want to say what are the properties for this domain that you can find. It's not always you can find an edge, that's for sure. Most of the time, actually, you don't find. So if you find an edge, which is harmonic, and it agrees with your potential outside your domain, what can we say about it? So that's the question. And again, and I repeat and stress, most of the time you don't find this. The boundary has to have some kind of regularity in order to get there. And that is actually the reverse question we're putting, that when you have this, what can you say about the boundary? Of course, if your boundary is analytic, Fg is analytic, then Cauchy-Kowalewska tell you that you have actually a solution to the problem, V equals to F with boundary values 0 and normal derivative G. This is just classical in a PD course you might even use, well, it may be advanced course, but when you have the Cauchy-Kowalewska. I think back in time, people did that, but nowadays, I don't think people do this anymore. Anyway, and now you go back to your UD and you see your Laplacian of UD was exactly this, correct? But if you cut V now, if you cut V with the characteristic function, so you put it 0, it's a pretty discontinuous function. Well, it's not discontinuous because V is 0 on the boundary. So the gradient is discontinuous. So the Laplacian of V is going to be this plus the extra measure. So they both will have the same Laplacian. Now, if you take the difference will be 0 outside D, because that was a condition for H. You find an H which is equal to UD outside. So the difference is 0 outside, and then H is going to be harmonic because Laplacian of this. So in the case of analytic boundaries, analytic boundary values, F and G, then you will actually have a solution. So this problem is meaningful in analytic case. Now, I will ask you, well, I don't think I asked you, I'm sorry. So my question would be whether the reverse is true, whether you start with something, everything F and G are analytic, but you don't know about the boundary of D. Is boundary of D going to be analytic? Because Cauchy-Kowalewska says, if you have analytic, you get a solution. I say, if you have a solution, it's a inverse problem. Well, inverse question, not the problem. So is the boundary analytic? And this question has been answered in variations. In 2 dimensions, more or less complete results. So let me tell you about one result that Alt-Caffarelli and Athanasopoulos, I'm used to Alt-Caffarelli functional. Athanasopoulos, Ioannis, and Luis and Sandro did this in 2001. this was originated in the work of Alessandrini and Isakov. So they said that when f is 0, so this was the hard part, when g is actually positive, that's the harder problem. And then you could get the potential is actually uniformly Lipschitz inside B1 half, and the boundary is going to be C1 alpha. So these are very complete results. So you could get from inverse conductivity problems in order to get this kind of result. They put it that way rather than unique continuations, but this is also connected to this unique continuation properties. So let me, I think I have probably one or two problems here I can tell you about in these connections. Okay, so, and yeah, if you want to see more about it, you can actually see scalar case and then vectorial case of these two papers that work with the potential single layer potentials. So it seems that the areas are deeply connected, although when I read techniques, they are actually very different. So somehow it's very good to bring people together like this to get new ideas and maybe connect mathematically. Okay, so let me recall again the Bernoulli problem. This is my slides from the beginning I had. So you have the two divergence here, and then you have this one. So the transmission problem is, so the transmission problem I just told you about is actually a two-phase Bernoulli type when G equals to 0. Am I right? Yeah, yes, yeah, exactly. So this is I'm just mentioning for you the connections. There's a little bit more general version here. Actually, you can work even for fully nonlinear PDEs. The techniques are going to be completely different then. Okay, so let me close that chapter and am I on the right way? Yes, and tell you about one system, another system here. So another system that we looked at some 5 years ago with Alessio and Sangen was so we went back to the problem that I told you about from the beginning, basically, but now we had a little bit different type of assumptions on D. And the question was whether you have, suppose you have a transmission problem, and suppose just simple transmission, even in scalar case. So you can think of in one part here in the domain, you don't know anything about regularity of D. So let me tell you that. But you know that U is Lipschitz in the D or outside D. So if U is Lipschitz on one side, is that regularity, is that Lipschitz regularity transmitted through the transmission problem on the other side? And if you think of the transmission problem that the gradients balance, if the gradient is Lipschitz on this side, it should force the gradient to be Lipschitz from the other side. And that is true when the boundary is smooth, but the boundary may not be smooth. So if the boundary is like having a cone-like things, is that going to be possible still? That this Lipschitz is transferred to the other side? And the answer is yes, that you actually have the gradient in B1 half is basically with the norm here, which is not important, and then the gradient on one side. So if one side has bounded gradient, so does the other side. So this is purely transmission problem in the sense of optimal regularity for the solution rather than the boundary. I have no information about the boundary, but I know my solution is going to be Lipschitz on one side of this region. And is that transmitted to the other side? And the answer is yes. And this was done for systems. We left open here again the regularity theory because this seems to be extremely hard. Our techniques didn't and don't work. They don't work for this problem. Or when you have a system scalar case, then you have to ask for D to be a level set, for instance, then it works. But if D is not a level set, well, we don't know that. Still, that would still be open. So this is an open question, and I would say probably hard question, but very interesting. Okay. So I guess this is my last transmission problem. And this is something that some of you, I'm sure, know about. This is Eshelby's problem. This is a very famous problem. I didn't know about this. This has to do with inclusions, and stress comes in. And then the question, I think Eshelby proved that in certain regime, I cannot the terminology, so in certain regime, no stress or something leads to ellipsoidal inclusion. So observe, to start with, your PDE is completely in Rn. Think of 2 dimension. So it's completely in Rn. At infinity, the solution behaves almost linearly. And inside the inclusion, the domain D, so the D is given to you. You don't have any information about it, but you know that there is a D. Inside D, you know that U is a linear function. So let's say x1, something like this. So U is a linear function inside D. Across the boundary, there is a transmission given like this, boundary of D. The whole PD, the PD holds in Rn. Asymptotically, U is linear function. So what can you say about this problem? Here shall we prove that ellipsoids answer, they are solutions. I'm sorry if I'm not very exact on who did what, because there is a range of results concerning this. I just want to connect to free boundaries. This was done already by people, so I want to connect to the obstacle problem. So conjecture is that this is actually the ellipsoids. So let me be faster. I see I'm losing time here very fast. So by playing around with this potential, so fundamental solution with the characteristic function, and then if you take the derivative of this, you just go inside, change the variable, and then you will have something like this. So from the equation we just had, I call it 5, the PD system we had, you can actually prove that this derivative of this function is linear function. But this is actually not so straightforward. There's a little bit of work. So I'm not going to go into that. You can find it in Kang's book. I think it's the book, yeah. You can find it. Is it the book or the paper? I'm not 100% sure. I'm sorry. But you can see that with a little bit of calculations, you can get that this is a linear function inside the D. Don't forget it. So what we want to do is to look at, instead of looking at the derivative, we look at UD. That is the function itself, which is a polynomial of degree 2 inside the D. Because it's a linear function, the primitive is a polynomial. And if you take the difference between the polynomial and the potential, then you will have exactly a formulation of the obstacle problem, a global obstacle problem. So the global obstacle problem was proven 23 while back in 30 years ago. Sakai proved in complete classifications. Recently, we proved in dimension larger than equal to 6, and then new results by Abel, Weiss, and Figali in annals this year came up with the dimension between 3 and 5, so they completed the result. So this is going to be kind of ellipsoids when it is bounded, and paraboloids if it's even unbounded. So you can talk about unbounded inclusion. So this is a branch one can actually think of to study Eshelby problems with unbounded in unbounded regime. So the domain is unbounded. Just give you a kind of a problem that might be interesting from a transmission point of view. So give me a few more minutes, I will finish with the scattering theory. It's more formulation rather than anything else. So this is a question that Mikko Salu came to me and asked more than 5 years ago, and then we have been discussing this and proving a few interesting results. It was has been very enjoyable to work with him, a very pleasant person, a great mathematician. So you think of the Dirichlet to Neumann map. I guess you're very familiar with this, most of you, I'm sure. So you think that you have a uniqueness of the solution of this, and then you look for, let me not be detailed here. So what you want to do is, a question that you raise is, what kind of, so you want to determine Q, that's the classical question. But of course, that's a very hard question. So what you do in a very specific case. So a question that I can tell you right away is that I'm going to come into that is, when you do measurements and whether you have a Q or not a Q, what kind of regions you can sort of see the difference of. Does your measurement see the Q or not? That was the question. It took me a while to understand the problem, but eventually we could do a little bit of work. So the question is whether you get this equality gives any information about these two. So we would discuss one Q and the other one to be 0. But before that, let me translate this to a free boundary problem. So once they are equal, observe, these are the normal derivatives of the solutions, U1 and U2. So lambda Q1 is the normal derivative on the boundary. So if you take the difference, the function is 0 on the boundary, the normal derivatives are the same, so the normal derivative is 0, and then you put the Laplacian, then you're going to get, the Laplacian is going to be g times characteristic function, where g is going to be exactly this. So this actually is a free boundary problem. If you look at this guy here, it's a free boundary problem. You have a g, characteristic function of a domain u is outside. That is classical, what we call obstacle type problem. There is a huge difference and very difficult one, is that this g changes sign, so does u. They change sign, and that was the difficulty. So that's the basic difficulty in this scattering problem. So the non-scattering problem, I think they called it non-scattering problem, is that you start with the lambda. So there's a wave here, and then you consider the two solutions here in 6, and then you assume they have the same normal derivative. It's like putting that this thing in H2 0. Okay, and then you want to see, and then let me skip this discussions. So the question would be, let me skip this discussion. The question would be a particular case when Q equals to H times characteristic of D, and H is a bounded function here. We usually take it holder. Now inclusion D is here inside, and then you will look at the PDE. It will be now much easier PDE, and you have this scenario. Laplacian of U is F. Now F is very specific and characteristic function of D. Still, you don't know what D is. Okay, so that D is the thing that you, after measurement, you want to find out if you can see that measurement with that D or not. Okay, so the setting is completely a free boundary setting. So you start with scattering, you end up with a free boundary. Okay, I give you the notes, you can check them later. I know it's going a little bit fast for you. I don't want to go over time. I'm sorry. I think I've done that, but anyway, a few more minutes. So here is the problem. After you run the whole show, you will get Laplacian of U is F times characteristic function of U is not 0. And this problem is, I mean, once we had characteristic function of U is positive was already very hard. Now you have, it is not, U could change sign. The worst thing is that also F can change sign. The good news is that F has some regularity. If you try to scale this, that F will eventually be a harmonic function. Without that, we cannot do anything. So you're expecting F to have zeros. So F has zeros, F can change sign, so does U. Now my question is, what kind of regularity are you expecting for the solutions? We have several papers in this regard. think you can find them, especially with all of them are basically with Miko and also Pujao. We have written several papers, Pujao call. So we have one forthcoming, hopefully next month, that tells us a little bit more about this situation when both signs are changing. And we seem to have some partial results, which I cannot express here. I don't even remember them because it was like we looked at it. So we're scan discussion. So it seems that this area with free boundaries and the scattering are really connected, and there are actually a lot of interesting things to bring from one to another and bridge. So thank you, and sorry that I went over the time.
Thank you very much. Thank you very much, Henrik, for the very nice talk. Are there any questions or comments, please? Please feel to unmute yourself. Any questions? Please, please. Please, please.
Oh, hello. Thank you for the talk.
Dimitras.
Yeah. I want to make a comment. In some papers of yours, both for scalar and vectorial free boundary problems, the singular strata seem to carry geometric structure reminiscent of Almgren's stratification in minimal surface theory. And I think that maybe if you try to formulate these singular free boundaries as stationary variables, possibly with generalized mean curvature given by the reaction terms or flux jumps in the PD, then maybe geometric measure theory tools like Allard's regularity theorem or Price rectifiability could be used to advance the partial regularity theorems. So this is a suggestion.
Yeah. Thank you. I think there are some push in those directions. Alessio and Sarah with Javier Rosoton, they have pushed that in that direction with the classification or stratification for this. But when there is no sign, we have resolved with Saint-Migeon, which is, we couldn't complete that because again, when there's a sign change, it becomes the technique doesn't work. So you have to do a little bit different things, and we couldn't come up with ideas. But we opened for others to maybe pursue that. So yeah, you're completely right. The methods from geometric measure theory are usually very helpful in free boundary.
Regarding your the solution pathway that these works followed, could you please comment on it a bit? Because I have some ideas on my own and would like to work on this. That's why I'm asking.
Could you repeat what the question was? This was the second question, or is it still the same question?
No, it is continuation of the prior question, because you said that there already exists work towards that direction.
Yes.
Could you please make some comments on this work? I mean, how does it proceed?
There is a paper by Figali, Serra, and Rosoton, and there is a paper by Figali and Serra, and then there is another one for parabolic versions with the three of them. So they use actually monotonicity formula, the frequency formula, Almgren's frequency formula, and pursue and classify. So the blow up, what they do is a blow up and a standard technique of blowing up. The problem is you do a linearized blow up. So it means you subtract something, a linear part, and you subtract the first blow up and you do the second blow up. And that brings the completely new free boundary problem. So you go from obstacle to what's called thin obstacle problem, and you have to start looking at those problems. So it's pretty technical, but you can find we can find the ideas written very well in the introduction of that paper. It's very, very well explained, but the techniques are a little bit different. But if you're familiar with geometric measure theory, I think it will not be hard for you to follow that.
Thank you very much. Can I ask a
I
final
hope it
question?
answers.
Yes, can I ask a final question?
For me, yes.
Yes. So
Yeah,
on
sure.
this topic, I mean, you just mentioned, you just commented with respect to the monotonicity, but I think what really seems to me as troubling is how the PD-driven curvature terms could be interpreted as a generalized mean curvature of the varifold. For me, this is the most.
Well, don't you have monotonicity formulas for minimal surface theory? I mean, that's probably what you have to look at.
Okay.
That's what I would. I'm not. I mean, I'm not an expert in those. I mean, I don't even know the area. So, but I think works of Delalis and his collaborators might be helpful for you because he's pushing more in that direction. Camilo Delalis. You should probably look at his papers because the language he's using is more geometric measure.
Thank you very much.
Yeah, you're welcome.
Thank you very much. Are there any other questions or comments, please? Please.
Yeah, so thanks for the very nice talk. And so I've been
Thank you.
working on this inverse scattering problem from the point of view of transmission eigenvalues and others. And there's some interesting phenomena that we've been trying to look at. And it's a situation when there's like the shape is polyhedral. So it's like in 2 dimension could be a polygon, for example. And what turns out is that when you're looking at the solutions to these kind of non-scattering waves, they tend to like vanish when the corner is like less than 180 degrees. But it turns out that numerically, if the angle is more than 180 degrees, they often tend to blow up. So have you ever seen anything like this in the free boundary, that depending on the angle of like polyhedra, you have like completely opposite behavior in some sense?
Yeah. Let me try to understand your question. So what you're saying is that the domain D, the inclusion or this object you want to find, is a polygon, correct?
Yeah. So we're looking at the situation where, so it's from the scattering situation, you have a solution, let's say Laplace plus k squared of u is equal to some function on this domain. And you assume that the Dirichlet-Neumann boundary data is 0. So it's one of these like non-scattering solutions. And numerically, so we can prove that if the polyhedron is convex, then this solution U must vanish at the corners. And but then numerically it seems
you mean the right hand side? No,
yeah. So the right hand side, will need to vanish also.
Okay.
Yes, yeah.
The right hand side will vanish.
Yeah.
Oh, I see. Because we assume that the solution doesn't vanish,
right,
then we get the free boundary condition, which are more or less correct. Now you're saying it vanishes. I see what you mean now. Okay. Yeah, I don't have a direct feeling. Do you have any paper you can suggest me to look at? Because I think I might have seen this, but I don't remember it where. Maybe I think it was one of your papers also. With you
I can send in the chat
some of your colleagues.
Or I can send by email after this talk, for example.
Yeah, that would be great, because I think we might have I've been thinking about it with Miko a little bit.
Yeah. So the thing that is like kind of completely like difficult. So we're working a little bit on this with Walter Pohjola. We are trying to understand the situation where the corner is more than 180 degrees, because then that would mean that somehow like the F would have like a blow up in this situation, at least numerically. And that is somehow very surprising.
Yeah, I see what you mean. Yeah,
Yeah.
yeah. I don't have any answer to that, but I think
Yeah,
the question is extremely interesting.
Yeah, okay. I will send
yeah.
you by email some
Thank you.
papers. Okay, thank you.
Yeah, that would be great. Thanks a lot.
Thank you very much. Any other questions or comments, please? Okay, if not, thank you very much, Henrik, for the very, very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you. Thank you.